People everywhere are caught up in the idea of settling Mars. Elon Musk talks about a city of 1 million people living there by 2050. NASA is preparing plans for astronauts to make the journey. Across the globe, there's this growing belief that Mars is our safety net, the place humanity will turn to if Earth fails us. But suppose the reality is far less hopeful. Suppose the fundamental rules that govern physics, the limits of biology, and even the way time shapes our lives are all working against that dream. What if the red planet isn't a new home waiting for us, but one of the most convincing illusions we've ever created? In this video, we're going to look directly at the hard scientific truths that are often pushed aside. The uncomfortable reasons Mars may never be more than a distant glow in the night sky. If you're willing to rethink what you've heard about our destiny among the stars and take an honest look at the science that defines what we can and cannot do, go ahead and subscribe and give this video a like. And let me ask you something. If you had the power to alter just one thing about the universe, what would you choose? Share your thoughts in the comments below. I'll pin the most imaginative response. Let's get started. Before we get into why Mars may be beyond our reach, it's worth recognizing something first. The drive that pushes us to even consider this idea is extraordinary. We are the species that stared at the oceans and learned how to cross them. We looked up at the sky and figured out how to fly. Now we look toward Mars and build rockets to reach it. That urge to explore is part of who we are, passed down from ancestors who left Africa and eventually spread across the entire planet. But Mars isn't simply another landmass waiting to be explored. It is a completely different world, and the obstacles it presents aren't just more difficult, they may be unlike anything humanity has ever dealt with before. So let's begin with the trip itself. On average, Mars sits about 225 million kilometers from Earth. But that figure hides the real complexity of the journey because both planets are constantly moving around the Sun. When Mars swings closest to us, the distance shrinks to roughly 55 million kilometers. When it's on the far side of its orbit, that gap stretches beyond 400 million kilometers. Because of this planetary motion, we can't simply leave whenever we choose. Missions to Mars depend on launch windows that open only every 26 months, when Earth and Mars line up in just the right way. The fastest spacecraft ever sent past Mars was NASA's New Horizons, which raced by at about 58,000 kilometers per hour on its way to Pluto. Even moving that fast, and even if Mars were at its closest point, the trip would still take more than 30 days. But here's the problem. Humans can't travel at those speeds. A crewed spacecraft must carry enormous amounts of fuel, food, water, oxygen, equipment, and protection from radiation. All of that extra mass means the journey becomes much slower. Based on current NASA concepts, a human mission would take around 9 months each way. That means 9 months sealed inside a metal vessel, exposed to space radiation, while your bones gradually lose strength and your muscles slowly waste away. Compare that to the Apollo missions, which reached the moon in just 3 days. 3 days versus 9 months. That difference isn't just about distance. It represents a completely new level of stress on the human body, pushing it toward limits it was never designed to endure. Yet distance alone isn't the biggest threat. Radiation is. Here on Earth, we're protected by a strong magnetic field and a thick atmosphere that shield us from cosmic rays and energetic particles from the Sun. The instant you leave that protective envelope, you're exposed to radiation doses that would be considered unacceptable for workers in nuclear facilities. During its cruise to Mars, NASA's Curiosity rover measured the radiation environment astronauts would face. A round trip would deliver a dose of about 600 millisieverts. That's roughly equivalent to getting a full-body CT scan every 5 days for a year and a half. This kind of exposure doesn't just raise the risk of cancer. It can damage the central nervous system, leading to problems with memory, decision-making, and motor control. Experiments on mice subjected to cosmic radiation have revealed serious brain damage and noticeable changes in behavior. These high-energy particles pass straight through the body, tearing through DNA, neurons, and the very cells that define who you are. And there's no easy fix. To block cosmic rays effectively, you'd need shielding made of meters of dense material like lead or water, which would make any spacecraft impossibly heavy. The situation doesn't improve once you arrive. Mars lacks a global magnetic field, and its atmosphere is only about 1% as thick as Earth's. Standing on the Martian surface, you'd absorb roughly 230 microsieverts of radiation every day, comparable to receiving a chest X-ray every 3 days. Over the course of a 2-year mission, that exposure would greatly increase the chances of cancer, cataracts, and infertility. Your DNA would be under relentless attack. But let's imagine, somehow, that future technology solves the radiation issue. Another problem immediately takes its place: gravity, or more precisely, the lack of it. Mars has only 38% of Earth's gravity. At first glance, that might seem appealing. You could leap higher and move more easily. But the human body evolved over millions of years under Earth's gravity. Every system we have depends on that constant pull. In microgravity, astronauts lose about 1% of their bone mass every month. Even aboard the International Space Station, where strict exercise routines are followed, astronauts return home after 6 months with serious losses in bone density and muscle strength. Mars's gravity would slow that decline, but it wouldn't stop it. After spending years there, bones could become dangerously fragile, and muscles too weak to function properly back on Earth. Returning home might not even be possible. You wouldn't just be living on Mars, you'd be medically confined to it. This gravity issue extends even further into reproduction and development. No mammal has ever been conceived, carried, and born in a reduced gravity environment. We simply don't know whether human pregnancy could succeed on Mars. The formation of bones and muscles, the development of the heart and blood vessels, and even the inner ear systems that control balance all depend on Earth's gravity. Remove that constant force, and the consequences are completely unknown. A child born on Mars could grow up with a heart that simply isn't strong enough to push blood against the pull of Earth's gravity. That child might never be able to set foot on the world their species evolved on. In trying to settle Mars, we could end up creating a permanent group of humans whose bodies are shaped by weak gravity. People effectively confined to Mars for life. And even if radiation exposure and low gravity were somehow managed, there is a quieter, more dangerous threat waiting there: the dust. Martian dust is nothing like the dust we deal with on Earth. It's unbelievably fine, with particles around 3 micrometers wide, small enough to slip deep into the lungs. It also carries an electrostatic charge, so it clings stubbornly to surfaces, fabrics, seals, and skin. More troubling still, it's poisonous. The soil on Mars contains perchlorates at concentrations roughly 10,000 times higher than what we consider safe on Earth. These chemicals disrupt the thyroid, interfere with hormone production, and can seriously affect development in children. This dust gets everywhere. The Spirit and Opportunity rovers were designed to work for just 90 days. Yet they survived for years, largely thanks to unexpected gusts of wind that cleaned their solar panels. Humans won't have that luxury. Every time you return from a walk on the Martian surface, you'd carry toxic dust back with you. It would slowly build up inside habitats, inside tools, and inside your lungs. NASA still doesn't have a reliable way to keep it out. Living on Mars would be like trying to survive inside a planet made of poisonous talcum powder that also sticks to everything. Mars's extremely thin atmosphere brings another set of challenges that border on the impossible. With atmospheric pressure at less than 1% of Earth's, exposure without protection would cause your blood to boil. You couldn't step outside wearing just an oxygen mask like you see in some sci-fi films. Every excursion would require a full pressure suit, and these suits are complex systems that can fail. A tiny tear, a bad seal, one small malfunction, and you would be dead in under a minute. The thin atmosphere also means Mars struggles to retain heat. At the equator, on a summer day, temperatures might briefly reach a pleasant 20 degrees Celsius at noon. By nightfall, they plunge to around -73 degrees Celsius. At the poles during winter, it gets cold enough for carbon dioxide itself to freeze out of the air, reaching -125 degrees Celsius. These extreme temperature swings happen every single the Martian day, placing enormous strain on habitats, machinery, and life support systems. Trying to grow food on Mars introduces difficulties that make Antarctica seem almost welcoming. Martian soil isn't just toxic because of perchlorates. It also lacks many essential nutrients and the beneficial bacteria that plants on Earth depend on. Lower gravity changes how water moves through soil and how roots develop. On top of that, Mars receives only 43% of the sunlight Earth gets, meaning many Earth plants wouldn't be able to photosynthesize enough energy to stay alive. In the film The Martian, Matt Damon's character grows potatoes in Martian soil mixed with human waste. In reality, those potatoes would absorb perchlorates and likely fail to grow at all, partly because the soil lacks the complex microbial life plants need. You'd have to bring soil from Earth or manufacture it, but soil isn't just dirt. It's a living system made up of thousands of species of bacteria, fungi, and microorganisms. Rebuilding that entire ecosystem on Mars may be beyond our capabilities. Water presents yet another enormous obstacle. There is water ice on Mars, at the poles and likely beneath the surface, but accessing it demands vast amounts of energy. You'd have to drill through frozen regolith tougher than concrete, melt the ice, and then purify water that could be contaminated with perchlorates and other toxic substances. The energy costs alone make large-scale water extraction extremely difficult. And unlike Earth, where the water cycle naturally cleans and redistributes water, on Mars every single drop would need to be carefully collected, processed, and reused by artificial systems. The psychological strain could be the most severe challenge of all. Mars sits, on average, 14 light minutes away from Earth. That creates a minimum 28-minute delay for any two-way conversation. You say hello, then wait 28 minutes to hear a reply. There would be no real-time conversations with family, no live technical support, and no immediate assistance during emergencies. You would be more isolated than any human has ever been. The Mars 500 experiment, which confined 6 volunteers inside a simulated Mars habitat for 520 days, offered a glimpse of this reality. Even though the participants knew they could leave at any time, had constant communication with the outside world, and faced no real danger, the psychological toll was intense. Crew members suffered from depression, sleep problems, and growing interpersonal conflicts. One participant withdrew almost completely, staying in bed for days and refusing to engage. All of this was on Earth, under Earth's gravity, breathing Earth's air, with the simple comfort of knowing that home was just a step away. On Mars itself, there is no such exit. If someone suffers a psychological collapse, there is no option to send them back. If deep, unresolvable conflicts arise within the crew, those people are confined together with no relief. Even the unchanging view could become unbearable. Endless red stone beneath a dusty pink sky, day after day without variation. Human beings evolved surrounded by forests, oceans, weather, noise, and unpredictability. We need living systems, change, and complexity. Mars offers none of that. It is lifeless, repetitive, and static, a kind of sensory isolation stretched across an entire planet. The medical realities of Mars are among the most unsettling factors to consider. On Earth, if someone has a heart attack, a stroke, or suffers a serious injury, modern medicine can reach them within minutes or hours. On Mars, the closest hospital is roughly 9 months away, and that's only when orbital mechanics allow a return. A fracture that would be inconvenient on Earth could become fatal on Mars. Appendicitis, kidney stones, infected teeth. Everyday medical crises that rely on rapid treatment cannot be properly handled with the limited tools and skills available on an interplanetary mission. Now imagine performing surgery in low gravity. Blood does not settle where surgeons expect it to. Fluids behave in unfamiliar ways. Even a highly skilled surgeon trained entirely on Earth would be operating in conditions that are completely alien, and that assumes a surgeon is even present. Early Mars crews may consist of only 4 to 6 people. You cannot bring specialists for every field. The onboard physician might handle emergencies, but not complex brain surgery, childbirth complications, or cancer. When problems fall outside their training, the outcome will be grim. The challenge of pharmaceuticals is just as severe. Drugs expire, and many break down faster when exposed to high radiation. Research aboard the International Space Station has shown that numerous medications lose effectiveness much sooner than they do on Earth. After 9 months of travel to Mars, followed by time spent on the surface, vital medicines could already be weakened or unusable. There is no way to restock. Every pill must be launched from Earth, predicted years in advance, and stored in an environment that actively damages it. Biological contamination creates a two-way problem that is rarely addressed honestly and carries profound risks. We often discuss preventing Earth microbes from reaching Mars, but the reverse is equally important. What if material brought back from Mars carries unfamiliar organisms? Even if the chance of life existing there is small, the consequences of introducing a Martian pathogen to Earth could be devastating. Every sample, every tool, every returning astronaut would require absolute quarantine. After Apollo, astronauts were isolated for 3 weeks despite the Moon being sterile. Any Mars-related quarantine would need to be far stricter. And here's the troubling twist. We may already have compromised Mars. Despite strict sterilization procedures, every rover and lander has transported Earth microbes. Certain bacteria and fungi can survive cleaning, space travel, and possibly even Martian conditions. If we discover life on Mars, how can we be sure it did not originate from Earth? That uncertainty could weaken the very scientific purpose of going there. The financial reality is harsh and often masked by hopeful rhetoric. The Apollo program cost roughly $280 billion in today's terms to place 12 people on the Moon for a combined surface stay of about 80 hours. A Mars mission would be vastly more expensive. Conservative figures suggest between $500 billion and $1 trillion for an initial mission alone. Establishing a self-sustaining settlement would demand tens of trillions over many decades. Even with promised cost reductions, the most optimistic estimates still place a Mars ticket at $500,000 per person, and that covers only the journey. It excludes habitats, air, water, food, and the enormous infrastructure required to stay alive. In truth, colonizing Mars would likely become the most costly project humanity has ever attempted, consuming resources capable of transforming life on Earth many times over, and the technological hurdles multiply rapidly. Reaching Mars is only the first step. Survival requires building an entire industrial base from nothing. Food must be grown. Fuel for the return trip demands a functioning chemical factory on the Martian surface. Equipment must be repaired, which requires tools and spare parts to be manufactured locally. Living space must expand, meaning construction materials have to be produced. Each necessity depends on specialized machines that must either be shipped across space or somehow created from raw Martian resources. The complexity stacks upon itself, turning Mars not into a refuge, but into one of the most demanding challenges our species has ever faced. Mars is wrapped in an atmosphere that's about 95% carbon dioxide. At first glance, that might sound ideal for growing plants, but at those levels it's poisonous to humans. To survive, people would need enormous sealed habitats with carefully regulated air, systems to keep everything warm through the brutally cold nights, and artificial lighting to make up for the faint sunlight that reaches the surface. Just supplying energy for all of that would be an immense challenge. Solar panels on Mars generate less than half the power they do on Earth, and they're frequently coated in dust that reduces their efficiency even further. That leaves nuclear power as a likely option, yet sending nuclear material into space brings serious safety concerns and political complications of its own. Then, there are the social and political questions, which may be even harder to solve. Who actually owns Mars? Who would be in charge of a settlement there? Which laws would people have to follow? The Outer Space Treaty of 1967 says that no country can claim ownership of any celestial body, but that agreement was created in a very different world. If a private company like SpaceX were to establish a colony, would it fall under US law? And what happens if the people living there decide they want independence? These aren't abstract thought experiments. They're deep, unresolved problems that could easily spark serious disputes or even armed conflict. The ethical side of this story is just as troubling. Is it right to terraform Mars, to reshape an entire planet, simply to make it comfortable for us? Do we have the moral authority to introduce Earth life and permanently contaminate another world? And if Mars already hosts native microbes, even very simple ones, do they have a right to exist without human disruption? These may sound like philosophical debates, but they directly affect how missions are designed and funded, and they could fuel strong political and social resistance to any attempt at colonization. One of the most underestimated obstacles is time. You often hear optimistic predictions about thriving Mars colonies in the 2030 seconds or 2040 seconds. Yet history tells a different story. Every major space project has taken far longer than expected. The James Webb Space Telescope was meant to launch in 2007, but it didn't reach space until 2021. The International Space Station was supposed to be finished in the 1,990 seconds, and in reality it wasn't completed until 2011. A Mars colony wouldn't just be slightly more difficult than these projects, it would be vastly more complex. Even if we launched an all-out Mars program today with unlimited resources, the first crewed landing would likely come in the 2040 seconds, and anything close to a permanent settlement might not appear until the 2060 seconds or 2070 seconds. By that time, climate change will have transformed Earth. Artificial intelligence will have reshaped society, and new technologies may exist that make the whole idea of living on Mars unnecessary. We're trying to plan for tomorrow using today's tools and assumptions. But the future rarely behaves the way we expect. The communications challenge alone is staggering. To stay in touch with Earth, you'd need relay satellites around Mars to maintain contact when the planet is hidden behind the Sunday. You'd also need a network of satellites in Mars orbit to link different locations on the surface. All of this would have to be built with redundancy, because if communications fail, a colony could be completely isolated from Earth for years. Constructing and maintaining such a system would demand dozens of launches and constant replacement, as equipment slowly breaks down under intense radiation. There's also a deeply uncomfortable possibility that few people like to confront. The human body may simply not be suited for long-term life away from Earth. Studies of astronauts have uncovered worrying changes we didn't anticipate. In microgravity, the shape of the eye can alter, causing vision problems that don't always fully resolve after returning home. Brain scans reveal structural shifts, with cerebrospinal fluid moving in ways that could have lasting effects on cognition. Some astronauts have even developed blood clots in the jugular vein, a potentially deadly condition that wasn't recognized as a risk until very recently. Reproduction raises even more serious concerns. A permanent colony can't exist without new generations. Yet we've never observed mammalian conception, pregnancy, or birth in reduced gravity. Experiments with mice on the International Space Station showed abnormal development and high death rates. On top of that, constant exposure to radiation could trigger genetic damage that makes healthy reproduction impossible. It's conceivable that we'll discover humans simply cannot reproduce successfully on Mars, turning any settlement into a one-generation experiment with no long-term future. Finally, there's the popular dream of terraforming. Some imagine we could turn Mars into a second Earth by releasing greenhouse gases, melting the polar ice, and building a thick atmosphere. The science paints a far harsher picture. Mars lost most of its atmosphere because it lacks a global magnetic field to shield it from the solar wind. Without that protection, any atmosphere we create would gradually be stripped away again. Generating an artificial magnetic field for an entire planet is so far beyond anything we can do that it borders on fantasy. And even if it were possible to thicken the atmosphere, the process would take tens of thousands of years at the very least. The notion that we'll one day reshape Mars into a livable world, while we're still actively damaging Earth's already finely balanced environment, might be the clearest example of human overconfidence. We struggle to take care of one planet's climate, yet we convince ourselves that we can design and control an entirely new biosphere on another world from nothing. And as we learn more about Mars, the idea of settling there becomes even less attractive. The Mars InSight lander picked up Marsquakes, showing that the planet is still geologically active. These events aren't driven by shifting tectonic plates like earthquakes on Earth. They're irregular, harder to predict, and could strike without warning, potentially damaging habitats and putting lives at risk. On the topic of new discoveries, if you're curious about how fast our picture of the universe is changing and why remaining on Earth might be the wiser choice while we continue to explore cosmic mysteries, take a look at my video called The Best James Webb Telescope Discoveries Until Now. The James Webb has revealed billions of worlds that could, in theory, support life. Many of them likely far more welcoming than Mars. You'll find the link in the description and on the card above. Now, let's carry on. The mystery of methane on Mars highlights just how little we truly understand that planet. The Curiosity rover has measured seasonal bursts of methane that could come from geological activity or from biological sources. If the source is biological, then we have a moral responsibility not to interfere or contaminate it. If the source is geological, it points to chemical processes we don't yet understand. Processes that might pose serious risks to human settlers. Either way, we're talking about moving people to a world we barely comprehend at a fundamental level. The challenges of returning samples from Mars expose how complex exploration really is. NASA and ESA are investing billions of dollars just to retrieve a handful of tubes filled with Martian soil, and that mission won't conclude until the 2032 at the earliest. If transporting a small amount of rock back to Earth is this difficult and costly, imagine how much more complicated it would be to safely send people there and bring them home. Getting back from Mars depends on producing fuel on the planet itself, using its thin atmosphere. Something we've never done on a large scale and something that could fail, leaving astronauts permanently stranded. The legal implications are equally unsettling. If SpaceX or another private company establishes a base on Mars, it effectively becomes a corporate settlement on another planet. History tells us what happens in company towns: exploitation, harsh conditions, and the erosion of basic rights. Picture being trapped on Mars, unable to return because you can't pay for the journey, forced to keep working in dangerous conditions because the same company controls your air and survival. That's not a fantasy scenario. It follows logically from the plans being discussed today. The cost of this dream is enormous. The trillions of dollars required to colonize Mars could instead be used to tackle climate change, eliminate hunger, cure diseases, and improve the lives of billions of people. We could create floating cities for those displaced by rising seas, develop fusion energy, and move toward an economy where basic needs are no longer scarce. Instead, we're captivated by the idea of sending a very small number of people to struggle and likely die on a cold, irradiated desert world. That's not forward thinking. It's a diversion from addressing the problems right in front of us. Life on Mars would also mean deep cultural and linguistic separation. Over generations, settlers would develop new accents, then entirely new languages. Their culture would slowly drift away from Earth's. They would feel foreign to us, and we would seem just as distant to them. The belief that humanity could remain unified across two planets is unrealistic when we can't even maintain unity on one. In time, Mars settlers would likely identify as Martians rather than humans, opening the door to tension or even conflict between worlds. The argument that Mars colonies would pay for themselves through mining and resource extraction doesn't survive serious examination. It costs roughly $10,000 per kilogram to send material to Mars, and potentially even more to bring anything back. There's no known resource valuable enough to justify those transport costs. Mining asteroids is far more plausible economically, and even that idea is filled with uncertainties. The claim that Mars will become profitable ignores basic arithmetic. Then there's the energy problem, which is often brushed aside in optimistic visions. A Mars colony would need constant power to heat living spaces through the long, freezing nights, run life support, operate greenhouses, power factories, and manufacture fuel for return trips. That demands a huge and reliable energy supply. Solar panels on Mars produce only about 43% of the energy they would on Earth. and global dust storms can cut that output almost entirely for months at a time. In 2018, a planet-wide dust storm lasted more than 3 months and blocked 99% of sunlight. Any settlement relying mainly on solar power would not have survived. Nuclear energy might seem like the answer, but it brings its own risks. Transporting enriched uranium or plutonium through Earth's atmosphere carries the danger of severe contamination if a launch were to fail. On Mars, you would need nuclear engineers just to keep the reactors running and safe. You would also have to manage nuclear waste on a world where you can't simply bury it somewhere and move on. A single nuclear accident on Mars wouldn't just be a setback, it could poison one of the very few regions suitable for human life, perhaps permanently. And this is where the challenge starts to repeat itself endlessly. Every fix creates another problem that demands yet another fix. The whole manufacturing problem becomes fractal. Take something as basic as concrete. To make it on Mars, you need water, but that water is frozen and mixed with contaminants. To clean the water, you need filters and chemicals. To make filters, you need advanced materials. To produce those materials, you need mining machinery. To build mining machinery, you need metals. To refine metals, you need extremely high-temperature furnaces. To power those furnaces, you need a huge, reliable energy system. And every single step in that chain depends on technology, skills, and resources that must either be transported from Earth or created from nothing on a hostile planet. So, let's talk honestly about the idea of Mars as a backup planet. The kinds of disasters people imagine making Earth unlivable: nuclear war, climate collapse, a massive asteroid impact, would still leave Earth far more habitable than Mars has ever been. Even a devastated Earth would still offer breathable air, tolerable atmospheric pressure, natural shielding from radiation, and liquid water on the surface. Any technology advanced enough to keep people alive on Mars could be used far more easily to help humans survive almost any catastrophe on Earth. In fact, underground shelters in Antarctica would feel like luxury resorts compared to living on the surface of Mars. Then there's the genetic bottleneck problem, and it's a serious one. A long-term human population needs enough genetic diversity to avoid inbreeding and dangerous genetic drift. Research suggests you'd need at least 10,000 people to maintain a stable gene pool, although some argue you might survive with as few as 160 if reproduction were strictly controlled. But controlling reproduction means deciding who is allowed to have children with whom. That leads straight into a totalitarian nightmare, a system that strips away basic human rights. A small Mars colony would be trapped between two grim options: genetic collapse or enforced reproductive control. The problems with muscles and bones go far beyond simple weakness. In Mars gravity, your entire cardiovascular system adapts. Your heart slowly shrinks because it doesn't have to work as hard. Your total blood volume drops. Your bones don't just lose density, they change internally, becoming weaker and more fragile. After spending years on Mars, coming back to Earth wouldn't just be uncomfortable, it could be deadly. Your heart might struggle to pump blood to your brain against Earth's gravity. You could break bones simply by walking. We would be creating a population of people whose bodies are no longer suited to life on their home world, people who may never be able to return. Experiments aboard the International Space Station have also shown that spaceflight accelerates aging at the cellular level. Telomeres, the protective ends of our chromosomes, actually grow longer in space, but then shorten rapidly once astronauts return. A pattern linked to aging and cancer. DNA damage builds up faster than it does on Earth. Radiation, altered gravity, and constant stress combine into a perfect storm for premature aging. On Mars, colonists might age 2 or even 3 times faster, meaning a 20-year mission could exact the biological cost of 40 or 60 years on Earth. The dust on Mars is another underestimated threat. Dust storms there can engulf the entire planet and last for months. The dust particles are incredibly fine, behaving almost like a liquid, slipping into sealed equipment and containers. They carry an electrostatic charge, so they cling stubbornly to every surface and are extremely difficult to remove. They are abrasive, slowly grinding down seals, joints, and moving parts. And they are toxic. containing perchlorates, heavy metals, and possibly other unknown substances that long-term exposure could turn into cancer risks or cause neurological damage. Psychologically, Mars would be brutal. It's a world of sensory deprivation. There's no rain, no snow, no real clouds, apart from thin, ghostly streaks, no animals, no plants, no meaningful seasons. The daytime sky is a strange butterscotch color, and sunsets glow green instead of red. The sun looks smaller and dimmer. At night, the stars don't even look familiar because you're seeing the universe from a different position. Every comforting signal that human evolution has wired into our brains is missing. It's alien in the most literal sense of the word. And then there's maintenance. On Mars, everything wears out faster. Extreme temperature swings cause seals to crack and fail. Metals weaken from constant expansion and contraction. Radiation slowly damages electronics. Solar panels lose efficiency as dust builds up. Mechanical systems grind themselves down under abrasive conditions. On Earth, we rely on entire industries to handle maintenance and repairs. On Mars, a small group of people would have to do all of it themselves, spending most of their time just keeping things from breaking, rather than exploring, building, or doing meaningful science. When you really stop and think about it, the ethical questions surrounding children on Mars become deeply disturbing. A child born on Mars never asked for that fate. They would be locked into a life where Earth is forever out of reach, where they will never feel the weight of an ocean around them, never climb a tree, never stand in the rain, never take a breath of air that hasn't passed through filters and machines. They would be born into a confinement they cannot escape, possibly into a body shaped by low gravity, too fragile to ever survive a visit to the planet their species came from. Is it morally acceptable to place a child in that situation? Do parents truly have the right to decide that kind of irreversible future for someone who hasn't even been born yet? The problem of contamination makes the situation even more troubling, and it cuts both ways with no real solution using today's technology. Each time astronauts step outside, they risk carrying Martian dust and any unknown microbes back into their living space. Every time equipment is repaired or maintained, Earth microbes are likely to be released into the Martian environment. Spacesuits don't remain clean. They become biologically polluted both inside and out. There is no realistic way to maintain perfect biological separation while still doing the constant work required to stay alive. Mars will be contaminated by us, and we will be contaminated by Mars. Food production on Mars is another crisis that looks far worse than the optimistic models suggest. To feed even a small settlement, you would need enormous greenhouses operating under flawlessly controlled conditions. Plants on Earth evolved alongside familiar patterns, clear day and night cycles, seasonal changes, and a specific spectrum of sunlight. Mars has a day that lasts 24 hours and 37 minutes, subtly but persistently disrupting circadian rhythms in both humans and plants. The sunlight is different too, missing wavelengths that plants rely on for vital biological processes. Even with artificial lighting, we would be fighting against millions of years of evolution. Hydroponic farming is often presented as the answer, but it comes with its own dangers. These systems depend on perfectly balanced nutrient solutions, non-stop monitoring, and regular replacement of parts that slowly degrade. One failed pump, one unnoticed contamination, one slight nutrient imbalance could wipe out an entire harvest. On Earth, when something goes wrong, we have backups, alternative suppliers, and the ability to bring food in from elsewhere. On Mars, there is no elsewhere. One agricultural collapse means starvation. The mental strain on the people responsible for food production would be immense, knowing that a single error could cost everyone their lives. Water recycling exposes an uncomfortable truth about daily life on Mars that glossy promotional videos rarely show. Every single drop of water would need to be reclaimed from urine, feces, sweat, and moisture in the air. The International Space Station manages about 93% water recovery, and even that system still depends on resupply from Earth. On Mars, efficiency would need to approach 100%. These systems would have to operate flawlessly for years without new parts. When failures inevitably occur, colonists could be forced to choose between dying of dehydration or drinking water that becomes progressively more contaminated. Then there is death on Mars, a subject most people prefer to avoid. Accidents will happen. Medical emergencies will occur. Some people will take their own lives. Systems will fail. When someone dies, what happens next? You can't bury a body in toxic Martian soil. Cremation demands huge amounts of energy that cannot be spared. Keeping bodies inside the habitat creates serious health risks and an overwhelming psychological burden. Some have proposed composting human remains to use as fertilizer, but that introduces pathogen dangers and an emotional horror few are willing to confront. The first funeral on Mars will shatter whatever illusions remain about it, being a shining new chapter for humanity. The idea that a Mars colony could easily manufacture what it needs also deserves serious scrutiny. Supporters often speak confidently about 3D printing and in situ resource utilization, as if these are fully mature, all-purpose solutions. In reality, 3D printing depends on specific raw materials, tightly controlled conditions, and can only produce limited kinds of objects. You cannot simply print electronics, seals, lubricants, or complex alloys. The vision of colonists mining ore, refining it, and producing advanced machinery from scratch is a fantasy. On Earth, with open air and abundant resources, it took thousands of years to develop metallurgy. Expecting the same to happen on Mars, inside spacesuits, with minimal tools, is unrealistic. The social reality of a Mars settlement would be equally dangerous. You would be confined with the same small group of people indefinitely, with no privacy, no way out, and no realistic hope of change. Every personal disagreement carries the potential to become a threat to survival. On Earth, people can change careers, move to new places, or build new social circles. On Mars, there is no escape. History shows us that even highly trained and carefully selected teams, such as polar explorers, remote military units, and submarine crews, experience serious psychological conflict. Now, imagine that pressure lasting not for months, but for entire lifetimes. Finally, there is the temptation of genetic modification, which reveals just how slippery the slope of Mars colonization could become. Some researchers have suggested altering human genetics to better cope with life on Mars, increasing resistance to radiation, improving adaptation to low gravity, or pushing even further into more extreme changes. Once that line is crossed, it raises profound questions about what it means to be human and how far we are willing to go in pursuit of a world that may never truly be meant for us. But following that path would mean shaping a fundamentally new kind of human, one that might no longer be able to reproduce with people on Earth. We would be splitting our own species apart, building permanent genetic divisions, and laying the groundwork for something resembling biological segregation. The moral consequences of that are enormous and deeply troubling. And matters get even worse when we look at what we're learning about Mars beneath the surface. Ground-penetrating radar has shown that the planet is riddled with vast underground caves and ancient lava tubes. At first glance, these sound like perfect natural shelters. In reality, they're complete geological mysteries. They could collapse without warning, contain poisonous gases, or involve chemical environments we don't yet understand. Exploring them would be extremely risky, yet avoiding them could mean ignoring the only places where humans might survive at all. It's a classic catch-22, one that could easily doom the earliest settlements before they ever become stable. The financial case for settling Mars collapses the moment you examine it closely. Supporters often mention exporting valuable minerals, selling scientific breakthroughs, or opening the planet to tourism. But the cost of transporting anything from Mars back to Earth makes trade essentially impossible. Scientific data can already be gathered far more cheaply and efficiently by robotic missions. And tourism? Asking people to spend millions of dollars for a 9-month trip just to walk in a bulky suit across a lifeless world is not a realistic business plan. The number of people willing and able to do that would be tiny. There is no sustainable economy here, only a vision that depends on endless financial support from Earth, indefinitely. Then there's the political reality. A permanent human presence on Mars would almost certainly ignite a new kind of colonial competition. Once one nation or corporation gains a foothold, others would feel pressure to follow, not to be left behind. That competition could quickly turn space into a militarized arena, undermine existing international agreements, and create tensions that don't stay confined to Mars. Even Antarctica, protected by treaties designed to keep it focused on science and peace, is already under strain from resource interests. Mars would face far greater pressure, with no practical way to enforce rules across millions of miles. The problem of time delay affects far more than simple conversations. Every part of running a colony would be shaped by it. Software patches, engineering advice, medical guidance, legal judgments. All of it would be slowed by a minimum 28-minute round-trip delay. In a crisis, the people on Mars would be completely alone. A serious software failure, a medical emergency needing expert input, or a life support system behaving in an unexpected way could turn fatal before Earth even receives the message. By the time help could be suggested, it might already be too late. Humanity has never faced isolation on this scale. When you compare this to what robots can do, the human settlement plan starts to look driven more by pride than practicality. Machines can explore Mars more safely, at a fraction of the cost, and with far greater efficiency. They don't need air, food, or protection from radiation. They can operate 24/7 and be built for very specific scientific goals. The results from Mars rovers have already been remarkable. Introducing humans multiplies costs enormously while often slowing science down, because so much effort goes into simply keeping people alive. If the aim is discovery, robots clearly outperform us. If the aim is settling Mars just to say we did it, we should seriously ask ourselves why. The gradual collapse of the human immune system on Mars would be a silent but devastating threat. Studies aboard the International Space Station show that even relatively short space missions weaken immunity. White blood cell levels fall, antibody responses decline, and dormant viruses, including herpes, can reactivate. This happens after only 6 months in low Earth orbit, where astronauts still benefit from some protection from Earth's magnetic field. On Mars, exposed to much higher radiation all the time, immune systems would suffer far more severe damage. A simple cold could become lethal. Any contagious illness could spread rapidly through a community with immune suppression comparable to that seen in advanced AIDS cases. Pregnancy and childbirth on Mars would be an even darker scenario. Radiation exposure during pregnancy would dramatically increase the risk of severe birth defects. Without advanced medical facilities, complications such as preeclampsia, breech deliveries, or severe bleeding would almost certainly kill both mother and child. Even in the unlikely event that a baby was born healthy, their developing body would be under constant attack from radiation. Their bones would grow abnormally in low gravity, their immune system would struggle to mature, and their vision could be impaired by unfamiliar light conditions. We would be deliberately bringing children into a world where disability is almost guaranteed. And finally, there's the dream of terraforming Mars, which falls apart when you look at the actual numbers. Mars has only about 1% of Earth's atmospheric pressure. To make the air breathable, we'd need to increase that pressure by at least 50 times and somehow transform carbon dioxide into oxygen on a massive scale. But all the carbon dioxide available on Mars, including what's locked in the polar ice caps and bound in rocks, could only produce an atmosphere about 7% as thick as Earth's. That's still far too thin to breathe and far too thin to warm the planet in any meaningful way. To go further, we'd have to haul enormous quantities of gas from elsewhere in the solar system, a task that would take millions of years even with the most optimistic technology we can imagine. The issue of the magnetic field simply has no easy solution. On Earth, our magnetic shield exists because molten iron deep inside the planet is constantly moving, generating a protective field around us. Mars doesn't have that luxury. Its core has mostly cooled and solidified, and that's why its magnetic field vanished billions of years ago. There are ideas about building an artificial magnetic shield at the Mars-Sun L1 point. But when you look closely, the scale is staggering. You would need a magnetic field generator comparable in size to a small moon, held in an incredibly precise position in space, operating without interruption forever. The energy demand alone goes far beyond anything humans have ever even planned for. And without a magnetic field, any atmosphere we manage to create would be steadily blown away by the solar wind over just a few thousand years. When scientists announced the discovery of recurring slope lineae, or RSL, on Mars, many people got excited, imagining flowing water. The truth is far less inspiring. These seasonal dark streaks are most likely caused by very small amounts of salty liquid, or even dry, grainy material sliding downhill. And if there is liquid water involved, it's so saturated with salt that it would be poisonous to all known forms of life. The salt levels are almost at saturation. Picture trying to drink water from the Dead Sea, except it's at -50 degrees Celsius and mixed with perchlorates. This is not the nourishing water of science fiction dreams, it's a chemically hostile brew. Living underground brings its own serious dangers. The risk of cave-ins is high and still poorly understood. Mars has a very different geological makeup from Earth, with unfamiliar rock types and stress patterns. Marsquakes happen regularly, and we don't yet understand when or why they occur. Going underground might shield people from radiation, but it also means trusting your life to geological conditions we can't reliably predict. If a collapse happens, the consequences would be devastating. There would be no heavy rescue machinery, no rapid way to dig survivors out, and no alternative shelter if your main habitat is destroyed. The idea that 3D printing will magically solve everything also needs to be grounded in reality. Today's 3D printers depend on highly specific materials, carefully engineered plastic filaments or metal powders with very exact characteristics. You can't simply scoop up Martian soil and expect a printer to turn it into useful tools. Producing proper printer feedstock from raw Martian material would require a full-scale chemical processing industry. On top of that, 3D printers themselves are complex machines made of hundreds of precision components that wear down and fail over time. When a critical part breaks, you can't just print the replacement if the printer is already down. It becomes a classic chicken and egg problem that promotional videos rarely acknowledge. The psychological toll would be unlike anything we've seen before. On Earth, seasonal affective disorder already affects millions of people simply because winter brings less sunlight. On Mars, the sun is weaker all year, the sky is never blue, and there is no natural environment to offer emotional relief. Research consistently shows that lack of exposure to nature increases depression, anxiety, and cognitive decline. Combine that with extreme isolation, cramped living conditions, constant danger, and the knowledge that there may be no return home, and you create conditions ripe for a severe mental health crisis. Suicide rates could rise dramatically, triggering further trauma among those left behind. Then there's the problem of equipment reliability, which only grows more severe over time. On Earth, we accept that cars need servicing every few thousand miles, appliances last perhaps 10 years, and even buildings require major repairs after a few decades. On Mars, every single system is essential for survival. Your habitat, life support systems, water recycling, power supplies, food production, communications, all of it has to function flawlessly all the time. But Mars is an unforgiving environment, and everything wears out faster. That means backups for every system, and backups for those backups, each adding mass, complexity, and new failure points. The cultural consequences of a small, isolated Mars settlement are rarely talked about. Human culture depends on diversity, constant interaction, and the steady arrival of new ideas. A colony made up of a few hundred people would be culturally starved. There would be no real-time flow of new music, art, or literature from Earth. No visiting performers, no cultural exchange, no immigration bringing fresh viewpoints. Over time, such a community could become closed off and unhealthy. History shows that isolated societies often drift toward rigid power structures, extreme conservatism, and resistance to change, which is hardly the vibrant future people imagine. Even the risk from asteroids is greater on Mars than on Earth. Mars sits closer to the asteroid belt and has a much thinner atmosphere, offering far less protection. The surface of Mars is covered in impact craters, evidence that large collisions happen regularly on geological timescales. Without a thick atmosphere to burn up smaller objects, even modest impacts could wipe out a settlement. Early warning systems would be limited, and there would be no practical way to deflect an incoming object or evacuate in time. Colonists would live under the constant threat of sudden destruction from the sky. Radiation damage on Mars goes far beyond an increased risk of cancer. It affects human biology at the most fundamental levels. High-energy cosmic rays don't just break strands of DNA. They trigger chains of free radicals that damage proteins, fats, and cell membranes throughout the body. The brain is particularly exposed and vulnerable. Recent research is painting a deeply troubling picture of what cosmic radiation does to the human brain. We're seeing evidence that it inflames brain tissue, breaks down synaptic connections, and causes proteins to fold incorrectly in ways that look disturbingly similar to Alzheimer's disease. After only a few years living on Mars, settlers would probably experience serious cognitive decline, memory problems, disorientation, shifts in personality, and eventually dementia. In effect, we'd be building a settlement where people slowly lose their mental clarity over time. And this crisis doesn't stop with the human brain. It spreads outward to the entire biological web we'd need to survive. A long-term settlement isn't just about having children. It depends on a working ecosystem. Bacteria to process waste, fungi to break down organic matter, insects to pollinate plants, and vast communities of microorganisms to keep soil alive. The problem is, we have no real understanding of how any of these life forms would behave or reproduce under Martian gravity and constant radiation. Nitrogen-fixing bacteria that plants rely on might fail entirely. The gut microbes humans need to digest food could mutate beyond recognition or simply die off. We could manage to transport people to Mars, only to watch the biological systems that keep them alive unravel. Now let's take apart the romantic idea of mining Mars by looking at real engineering limits. Mining requires heavy machinery, excavators, transport vehicles, crushers, and processing systems. All of that equipment depends on hydraulic fluids that would freeze in Martian cold, lubricants that would evaporate in the thin atmosphere, and seals that would harden, crack, and fail. Metals become brittle at extreme low temperatures. Fine dust gets into everything. Machines designed to last for decades on Earth would likely break down within months on Mars. And when something fails, there's no warehouse of spare parts to call on. To keep mining equipment running, you'd need a full industrial supply chain already in place, which itself depends on even more mining equipment. It's a self-defeating loop with no realistic starting point. Energy storage creates another seemingly unsolvable barrier. Solar panels only produce power during the day, and Martian nights are long, bitterly cold, and unforgiving. Batteries lose efficiency quickly in extreme cold. Repeated temperature swings cause materials to expand and contract, snapping connections and cracking components. Chemical batteries steadily lose capacity. Mechanical systems like flywheels demand near-perfect vacuum seals, and fuel cells rely on water that a colony simply can't afford to waste. Nuclear reactors appear to be the only reliable alternative, but they come with their own risks. They need cooling systems, generate radioactive waste, and require highly trained specialists to maintain them. A single major reactor failure could leave a settlement frozen and powerless in complete darkness. Mars itself adds another threat that's easy to underestimate. New analyses of Martian weather show that global dust storms carry strong electrical charges. These aren't just storms that block sunlight. They're planet-scale electrical events capable of damaging electronics, knocking out communication networks, and destroying solar infrastructure. Static discharges could shock or even kill astronauts inside their suits. Triboelectric charging could trigger explosions in fuel production systems. We currently have no technology that can reliably shield an entire settlement from electrically charged storms that can last for months. One severe event could erase a colony's technological backbone in a single blow. Then there's the issue of bones, which turns out to be far more serious than early estimates suggested. It's not just a gradual loss of bone density. In low gravity, the internal architecture of bone itself changes. The trabecular structure, the spongy framework that gives bones their strength, breaks down first. Joints that normally bear weight, like hips and knees, degrade at alarming rates. The most frightening aspect is that this damage may not be reversible. Studies of astronauts indicate that even years after returning to Earth, bone structure doesn't fully recover. People living long-term on Mars wouldn't just come back weaker. By Earth standards, many would be permanently disabled. The dream of self-sufficiency collapses completely when you look at modern manufacturing. Producing computer chips requires ultra-pure silicon, rare earth elements, and fabrication plants that cost billions to build on Earth. Constructing those facilities demands extreme precision machinery. Building that machinery requires specialized alloys. Producing those alloys means having a full metallurgical industry in place. Each step depends on massive infrastructure, deep technical expertise, and materials that may not even exist on Mars in usable form. The notion that a small, isolated settlement could recreate this technological ladder is simply unrealistic. Any advanced technology would have to be shipped from Earth indefinitely. Finally, there's the human factor. A Martian settlement would be an extreme social experiment under constant pressure. Isolated groups with limited resources tend to develop rigid hierarchies, hoard critical supplies, and divide the world into insiders and outsiders. Add the stress of knowing that a single mistake can be fatal, and you create conditions that encourage authoritarian control. Leaders would effectively hold power over who lives and who dies. Disagreement could be punished by cutting food supplies or assigning people to dangerous tasks. True democracy depends on freedom to move and to associate freely. On Mars, leaving the community means death. Under those conditions, colonies wouldn't drift toward dictatorship. They'd arrive there almost by default. The genetic bottleneck, when you look at it through the lens of mathematics, is unforgiving. Even if you begin with a population chosen with extreme care, random genetic drift would still wipe out diversity at a frightening pace. Damaging recessive traits would start appearing more often. After only a handful of generations, inherited disorders would rise sharply. The colony would be pushed into a terrible dilemma: either impose a controlled breeding system that tramples basic human rights, or stand by as their children face growing waves of genetic disease. There's no gentle outcome here. Only two grim possibilities: an authoritarian breeding regime or a society burdened by widespread hereditary illness. The problem of time itself would begin to pull human society apart. A day on Mars lasts 24 hours and 37 minutes. Close enough to feel familiar, yet different enough to matter. That small mismatch adds up every single day. After 1 month, Martian time would be an entire day out of step with Earth. Keeping schedules aligned would become harder and harder. Over time, settlers would slip further away from Earth's rhythm. When you add the communication delays, the sense of isolation deepens. People on Mars would quite literally exist in a different time frame, and that alone would drive rapid cultural and social separation. When you study the figures closely, the dream of closed-loop life support falls apart. Even the International Space Station, backed by constant support from Earth, cannot fully recycle its resources. Around 10% of its water is still lost, fresh air must be regularly supplied, and waste has to be managed externally. On Mars, survival would demand recycling systems that are almost flawless, operating for decades without replacement parts. Every tiny leak in a seal, every clogged filter, every failed pump means a permanent loss of vital resources. Over time, the settlement would edge closer to suffocation, dehydration, or starvation as these systems slowly wore down. The collapse of the human microbiome is one of the most overlooked existential dangers of living on Mars. We are not solitary organisms. Each of us is a moving ecosystem, carrying trillions of microbes that are essential to staying alive. They help us digest food, create vitamins, support our immune systems, and even affect our mental well-being. On Mars, constant radiation, reduced gravity, long-term isolation from Earth's microbial diversity, and an ultra-clean environment would severely damage this delicate balance. Weakened immunity would lead to more frequent antibiotic use, which would further wipe out helpful bacteria. Within a few years, settlers could face malnutrition despite sufficient calories, immune system disorders, and potentially lethal failures of the digestive system. The spare parts problem exposes just how impossible true self-sufficiency really is. A modern living habitat depends on thousands of highly specialized parts. Seals, bearings, circuit boards, filters, valves, sensors, all of them wear out in different ways and on different timescales. Mathematical models show that even a small community of 100 people would need millions of spare components to keep basic life support systems running for 50 years. The sheer mass of those parts would be far beyond what Earth could realistically send. Producing them locally would require hundreds of advanced industries. If even one crucial part couldn't be made or replaced, the entire colony could fail. It's a logistical nightmare that planning alone cannot overcome. Then there is the reality of nuclear power, a subject often glossed over by Mars enthusiasts. Small modular reactors sound ideal at first, but the details tell a different story. They rely on highly enriched uranium or plutonium, substances so hazardous that a launch failure could spread contamination through Earth's atmosphere. On Mars itself, cooling becomes a serious challenge. Reactors need water or gas to shed heat, yet water is scarce, and the planet's thin atmosphere is terrible at carrying heat away. Routine maintenance demands specialized tools and highly trained experts. Refueling depends on a supply chain that simply doesn't exist. Nuclear waste would have nowhere safe to go. It would poison some of the very few regions where humans could realistically live. An agricultural collapse is also waiting in the shadows, driven by how little we truly understand plant life outside Earth. Plants evolved under Earth's gravity, magnetic field, radiation environment, and light conditions. On Mars, roots grow strangely, water behaves unpredictably in soil, and photosynthesis becomes less efficient. The biggest obstacle, though, is reproduction. Many crops depend on specific pollinators or environmental signals to produce fruit. Without Earth's seasonal cycles, changes in day length, and familiar atmospheric pressure, many plants may simply fail to yield food. Genetic engineering could offer partial solutions, but that would demand a level of biotechnology infrastructure far beyond what a small colony could maintain. Recent research into the psychology of people living in confined environments points to deeply troubling consequences for any long-term human presence on Mars. The Mars 500 study revealed something deeply unsettling. Even a group of carefully selected, highly driven volunteers, placed inside a simulated journey to Mars, began to suffer serious psychological strain. Problems with sleep emerged. Depression set in. People withdrew from one another. One participant deteriorated to the point where he effectively disengaged and stopped taking part at all. And this happened here on Earth, under full gravity, with instant communication, and with the comfort of knowing they could step outside whenever they wished. Real settlers on Mars would face conditions far harsher than this, with no way out. Acts of extreme violence, severe psychotic episodes, and the collapse of social bonds wouldn't be distant possibilities. They would be likely outcomes. The crisis involving children goes far beyond questions of physical growth. For healthy mental development, children need varied social contact, rich learning environments, and regular contact with the natural world. A settlement on Mars could offer none of that. Young people would be raised in sealed habitats, surrounded by the same limited group of adults, without animals, without weather, without changing seasons. Research on children raised in severely constrained environments consistently shows deep developmental harm, difficulty forming relationships, and long-term mental illness. Such a colony would be raising a generation shaped by isolation, unable to connect in normal human ways. Then there is the problem of tightly linked systems, where failure spreads like falling dominoes. Every part of a Martian habitat must operate together perfectly. Oxygen supply, electricity, water recovery, climate regulation, communications. If one begins to falter, pressure builds everywhere else. A drop in water recycling efficiency means more energy is needed to process supplies. That increased demand weakens the power grid, leaving less energy for heating. Colder conditions damage seals and drain batteries faster, leading to further breakdowns. Each fault feeds into the next. On Earth, we manage these chains with backups and vast resources. On Mars, a single weak link could bring down the entire settlement. Governance and crime introduce another layer of instability. Imagine a serious crime taking place on Mars. Who would handle the investigation? Which authority would bring charges? Under what legal system would judgment be passed? And where would punishment be carried out in a place where every room, every structure, is vital for survival? International space law offers only vague guidance. A colony would need law enforcement, courts, and detention facilities, all of which would consume resources needed simply to stay alive. Yet without rules and enforcement, conflicts could quickly turn violent. The first major crime would plunge the colony into a permanent state of tension, with no clear way forward. The promise of building and manufacturing on Mars also collapses under scrutiny. On Earth, even the simplest electronic device depends on materials sourced from across the planet, involving countless suppliers, specialized factories, and skilled workers. Expecting a small off-world settlement to recreate this web is unrealistic. Mars lacks rare Earth elements, specialized metals, and many essential chemicals. Any missing component would either have to be shipped from Earth, undermining the idea of independence, or replaced with inferior alternatives that risk lives. Self-sufficiency would remain an illusion. There is also the question of how humans themselves would change. Mars presents a very different environment, with lower gravity and higher radiation levels. Over generations, natural selection would push Martian humans in directions unlike those on Earth. Traits that helped survive radiation or low gravity might come at the expense of others. Gradually, these adaptations could make Martian populations physically and biologically distinct. This wouldn't just be the creation of a new settlement, but the beginning of a separate offshoot of humanity, one that might eventually see Earth's people as something fundamentally different. Such divergence carries the risk of humanity breaking apart at its roots. Communication adds yet another barrier. The issue isn't only the delay in signals traveling between planets, but the structure of shared knowledge itself. Earth's networks of information, from scientific research to technical guidance, would not be available instantly. A Mars settlement would need its own copies of essential knowledge, but keeping them current would be impossible. Textbooks, research papers, instructions, all would slowly fall out of date. Over time, the colony's understanding of science and technology would drift away from Earth's progress. Within a few decades, they would be working with obsolete information, trapped in a snapshot of the past. And this brings us to the most persistent illusion of all, the belief that Mars is humanity's next great refuge. The red planet is not a spare version of Earth waiting to be claimed. It is an environment stacked against human life, disguised by excitement and ambition. Every challenge feeds into the next, forming a network of obstacles that optimism alone cannot undo. We're not dealing with minor technical hurdles that clever engineering can eventually fix. What we're up against are deep, fundamental mismatches between how the human body works and the reality of Mars itself. The strain on the human body wouldn't be a single problem you could isolate and manage. It would pile up over time, triggering a chain reaction of breakdowns that would ultimately destroy any long-term settlement. Radiation would steadily damage DNA and brain tissue. Reduced gravity would slowly erode bones and muscles. Fine, toxic dust would work its way into the lungs. Long-term isolation would grind down mental health. The immune system would weaken. The delicate balance of the human microbiome would collapse. These aren't independent issues you can tackle one by one. They amplify each other, turning into a combined catastrophe. After 5 years on Mars, a colonist would likely be mentally impaired, physically disabled, emotionally shattered, and suffering from multiple organ failures. That's not colonization. It's a slow-motion mass suicide, carried out at a cost of trillions of dollars. The recent enthusiasm for colonizing Mars, especially from billionaires, exposes an uncomfortable reality. This isn't really about the survival of our species, it's about ego. The people promoting this vision won't be the ones risking their lives on the red planet. They're marketing a fantasy they will never have to live through, financed by resources that could be used to fix real, urgent problems here on Earth. It's a stark display of privilege, trashing our own planet while dreaming of escape to another world that is already lifeless. The engineers and scientists who actually go to Mars would be the ones paying for these dreams with their lives. Think about the opportunity cost in human terms. The trillions of dollars required to establish even a basic Mars colony could instead provide clean drinking water for everyone on Earth, eliminate malnutrition, cure multiple diseases, and still leave enormous funding for education and infrastructure. We could build floating cities for people displaced by climate change, advance fusion energy, create vertical farms capable of feeding billions, and repair damaged ecosystems across the planet. Instead, the plan is to send a few dozen people to slowly die on a world that will never, and can never, truly support human life. The laws of thermodynamics make this unavoidable. Life on Earth survives because of constant energy flows. Sunlight powering plants, plants feeding animals, ocean currents moving heat around the globe, geological cycles recycling nutrients. Mars has none of this. It's thermodynamically dead. To create artificial energy flows that would demand more energy than any colony could realistically generate. It's like endlessly forcing water uphill, possible in theory, but hopelessly inefficient and unsustainable. Any Mars settlement would be an energy sink, burning through vast resources just to maintain tiny pockets of life surrounded by a planet-sized desert of death. Then there's the temptation of genetic modification, which reveals another danger. As conditions become more extreme, pressure to alter human biology would grow irresistible. Resistance to radiation, adaptation to low gravity, changes in digestion, even alterations to vision for different light conditions, each step pushing Mars-born humans further away from those on Earth. Over centuries, they might no longer even be the same species. That's not humanity expanding into space. It's humanity splintering into incompatible offshoots. People often point to extremophiles on Earth, organisms that thrive in environments once thought uninhabitable, as evidence that life could adapt to Mars. But this misses a crucial point. Those organisms evolved over billions of years to survive very specific extremes. Humans don't have that time, and genetic engineering can't compress billions of years of evolution into a few generations. We aren't extremophiles. We're fragile beings who require an incredibly narrow set of conditions to stay alive. Mars isn't just uncomfortable for us. It lies completely outside the boundaries of human survival. The philosophical consequences strike at the core of who we are. If we can't survive on Mars, the most Earth-like planet in our solar system, then it means something profound. The universe isn't cruel, it's indifferent. Earth isn't merely our birthplace, it's the only home we will ever have. Accepting that isn't surrender, it's understanding. Knowing our limits helps us focus on what truly matters, caring for and protecting the one world where life is known to flourish. The myth of Mars colonization distracts us from the real challenges humanity faces: climate change, collapsing ecosystems, inequality, global disease. These are problems we can actually solve if we commit the resources and attention they deserve. Every dollar poured into Mars dreams is a dollar taken away from healing Earth. Every brilliant scientist designing Martian habitats could instead be working on sustainable habitats here at home. We're obsessing over Mars while Earth burns. Accepting that Mars colonization isn't possible would be culturally shocking, but ultimately freeing. Without the illusion of escape, we'd be forced to face our responsibilities, here, now, on the only planet we have. Rather than treating planets as things we use up and move on from, we would learn what real sustainability actually means. Instead of thinking in terms of cosmic conquest, we would adopt a sense of cosmic humility. Humanity isn't meant to scatter endlessly across the universe. Our role is to care for Earth, to look after the only world we know that can think, feel, and ask questions in a universe that is otherwise silent and unaware. I want to leave you with a simple idea. Earth isn't just the place where we ended up by chance. It's the place we truly belong. Every atom that makes up your body was created inside stars and patiently brought together by Earth's living systems over billions of years. You're not simply standing on Earth. You are Earth, briefly arranged into a human being. Mars isn't the next great chapter of our story. It's a distraction that pulls our attention away from writing the next chapter of Earth's story properly. The reality is both sobering and inspiring. We are not going to Mars in any deep, lasting, or sustainable sense. And that's perfectly fine. We already have a whole planet right here that urgently needs our focus, our creativity, and our care. The very technologies designed with Mars in mind, closed-loop life support, smart recycling systems, clean renewable energy, have the power to reshape life on Earth and make it better for every living thing. The real challenge isn't finding a way to leave Earth behind, it's learning how to deserve it. So when you hear someone describe Mars as humanity's backup planet, remember this: Earth isn't just the best option we have, it's the only option we have. Mars will remain what it has always been for us: a striking point of light in the night sky, a destination for robotic explorers, and a reminder that in the immense universe, there is nowhere quite like home. Our future isn't waiting somewhere far away among the stars. It's right here on the pale blue dot that Carl Sagan reminded us is the only home we have ever known. And that isn't a restriction, it's an open invitation to make this world everything it has the potential to be.